Welcome back. This time we are going to learn the basic concepts of the k-nearest neighbor algorithm. From the previous video, we have learned how to think of examples as vectors in a high-dimensional space. Now we can apply geometric concepts to machine learning. One of the most basic geometric concept we can do in a vector space is computing the distance. In particular, we are going to look at the Euclidean distance. In general, in a d-dimensional space, the Euclidean distance between vectors a and b is given by this equation, where distance is just the square root of the summation of squared differences for each dimension. Let's see this equation in action. Consider this three-dimensional space. So we have here two vectors a and b, and to use the equation to solve for the distance between these two vectors, first let us transform the equation so that we can use it for 3 dimensions. And then let's just use the square root form. And now we substitute the values from 2 points to corresponding dimensions. So this one is a sub 1, this is b sub 2, b sub 1, a sub 2, and b sub 2, this one over here. And then a sub 3, and then b sub 3. And then just a simple manipulation of numbers, we get 0.9 as the distance between these two vectors. Now let's look into how we can use that in the nearest neighbor algorithm. So let's consider this data set. We have here a collection of training data, each with labels, and the labels are positive and negative. So as you can see, there's a test point here. If you are given the task to guess for the correct label for this point, what would your guess be? So you most likely have decided that the label is also positive. You would think so because we believe that the label for an example should be similar to the label of nearby points. Since the nearby points here are all positive, then it just makes sense that this is also positive. So this is an example of a form of inductive bias portrayed in nearest neighbors, and this is the concept on which the nearest neighbor classifier is built upon. Compared to decision trees algorithm, the nearest neighbor algorithm is ridiculously simple. So at training time, we store the entire training set, and then at test time, we get a test example, say x hat. So this is our test example, and this is our test point where we have to come up with a y hat, or our prediction. To predict its label, we find the most similar x, or in particular, we just get the closest training example x. Then we just use the value of y, which is the label of that x closest to x hat, and just use that as our prediction, or the value of y hat. Despite its simplicity, this nearest neighbor classifier is incredibly effective. However, it is particularly prone to overfitting. So overfitting happens when the model has learned too hard or too much. that it included noises or includes noises instead of only considering the useful information or data. Because these noises are included when the model comes up with a prediction, the prediction is no longer that reliable. So consider the following dataset. It has the same concept as to the previous dataset we had, but this time the test point indicated by the question mark is somehow in a tricky place. So knowing that the closest neighbor is positive, so let's say this is the closest x. So this is our x hat, and let's say this is the nearest x, and the label of that nearest x is positive. However, we can see that other nearby points have negative labels, and it makes more sense to say that the label is positive. And since the algorithm currently only looks at the single nearest neighbor, it is not able to evaluate the fact which is given by the majority. So a solution to this problem is to consider more than just the single nearest neighbor when making a classification decision. We can consider the k nearest neighbors and let them vote on the correct class for this test point. So let's say we consider the 3 nearest neighbors of the test point. So this is the test point, and this is the first nearest neighbor, which has the label of positive. So let's just put it x sub 1, and this is x sub 2, and this is x sub 3. So as we can see, through voting, negative would win, right? So with those things in mind, let's formalize the algorithm for the k nearest neighbor. So in lines 2 to 4, we just compute the distances from the test point and just store it in some array. So yeah, compare the distances of our x hat. So x hat is our test point. Compare these to all of our training data and get the distances, and then store the distances to this array indicated by S. And then in line 5, we just sort the distances so that we can get the k nearest neighbor. So let's say our k nearest, or the k value here is 3, and let us also, like for this example, assume that we have 10 data points and k equals 3. And then let's say after sorting the distances and getting the 3 nearest training data, let's just say we have come up with, or we have ended up with the first k nearest training example to be positive, the second nearest training example is negative, and the third nearest example is a negative. So let's say we have a positive, a negative, and another negative. So that's our 3k, or 3 nearest neighbors. And so in lines 7 to 9, it's just a simple trick to get the majority of, let's just say, majority of votes. We just assign value of 1 for each, and then add them all up, and the sign of the sum of this. So we add them all up, and the sign we get from that sum is just our prediction or the label, either positive or negative. Because of course, if you have more negative, which would be the majority of your k nearest neighbors, then you would expect to get a negative sign when you add them all up. So yeah, that's how simple the algorithm is for the k nearest neighbor. So to end this video, let's take a look at some aspects where the k nearest neighbor or neighbors differs from decision trees. So one aspect is that it assumes that nearby points should have the same label. Another aspect, which is quite different from decision trees, is that all features are equally important. So recall that for decision trees, the key question was which features are most useful for classification. And that is why in our decision trees we have that step of knowing scoring first the features and then selecting the features which has the highest score. However, in k nearest neighbors, all examples are used equally, all features are used equally. So in the next video, we are going to look at why that would be an issue for this algorithm. And then we are also going to look at another issue with this algorithm, which is called the feature scale. And yep, I think that's all. And thanks for watching.